Hi, my name is Andre Wang. I'm an assistant professor of psychology at the University of Toronto. These days, power analysis is often required for empirical studies, but it can be challenging to do, especially for complex statistical techniques like structural equation modeling or SEM. Part of the challenge, much like power analysis for simpler tests like t-tests and ANOVAs, is figuring out what effect size to power your study for. But when it comes to power analysis for SEM, there's actually a more fundamental question that we need to answer, which is what kind of effect we want to detect. When we conduct SEM, we typically care about both model fit, which reflects how well or poorly our model describes data, and target effects, which are particular parameters in our model that we are estimating, such as a regression coefficient between two latent variables. And here's the thing. These two kinds of effects reflect separate power considerations. You might be well powered to detect a certain level of model misfit, but not powered enough to detect target effects, or vice versa. One does not imply the other. Moreover, because any target effect is embedded in a model, characteristics about the model, even if not central to your hypothesis, can nonetheless affect the power to detect your target effect, which is what you care about. For example, if you want to detect a standardized regression coefficient of 0.2 in this model, your power might be higher than 0.8 when you have highly reliable factors and lower than 0.3 when you have unreliable factors, even at the same sample size. So what should you do? I propose that your power analysis should reflect your hypotheses. If you hypothesize that a certain effect exists in a model that you plan to interpret, then you should power your study to both detect that target effect and to retain your model. Insufficient power for the target effect means you have lower probability of finding a true effect. In other words, increasing your type 2 error rate. Insufficient power for detecting model misfit means that you have lower probability of detecting true model misspecification. In other words, missing true problems with your model, which in turn make your model less interpretable. The first kind of power, the one you see on the right side of the slide, likely makes intuitive sense to you. After all, it parallels what we do for simpler models like t-tests, ANOVAs, and regressions. The second kind of power might sound confusing. Why do we want to have enough power to detect misfit? Shouldn't we want good fit? Well, we do want good fit, but we can't know what's good until we define what's bad. More precisely, what's bad enough that we would question the validity of the model. So even if we might not want to detect model misfit, we should decide, ideally a priori, what our threshold for good and bad fit is. Deciding what counts as good fit can introduce researcher degrees of freedom, which in turn threatens the robustness of model interpretations and opens the door to fit hacking. But how exactly do you run both kinds of power analysis? Fortunately, as more resources for power analysis and SEM become available, it is now easier than ever to conduct sensible power analysis that reflects the complexity and flexibility of your particular model. Along with my collaborator Michael Remtula, I created one such resource. This is a free, open-access web application called PowerSEM. PowerSEM offers a user-friendly interface for conducting power analysis that is tailored to your particular structural equation model based on Monte Carlo simulations. If you have not run Monte Carlo simulations before, fret not. The app runs the simulations in the background and helps you with the process in the foreground via a 4-step procedure. First, you specify your model. Second, you visualize and confirm the model. Third, you input the parameter values of your model. Fourth, you set the sample size and run your power analysis. This app supports analysis for both types of power I just described so that you can identify a sample size that gives you enough power to both detect your target effects and ensure your model is robust against bad fit. This field guide will be available as a preprint soon, and meanwhile, you can check out the app and the accompanying paper. Thanks for listening, and feel free to reach out anytime.